So far, all of the examples we've done with static equilibrium have been with tension. Tonight, I want to walk you through how to do a problem if your object is on a ramp. And this is also going to stretch your brain a little bit with how you use sine and cosine, because sine and cosine aren't going to work out neatly like they usually do. So you're used to y always being sine and cosine always being x. Not going to work out exactly like that tonight. So here's our example. We have a block with mass m at rest on a ramp. I want to draw the free body diagram and write the equations for equilibrium. So you've seen this before. Let's work through it. So first, my free body diagram. Here is my object, the box. There is a force of gravity here. There is a normal force. And tonight we're going to go ahead and acknowledge that force of static friction. Anytime you have an object sitting on an incline and it's not falling down the incline, there is a force of static friction. So now that you've calculated those, shouldn't be too hard. Box on an incline, it's not falling down, therefore there must be a force of static friction keeping it from falling down that ramp. So there's my free body diagram. And now I need to write the equations for equilibrium. Up forces equal down forces, and left forces equal right forces. Okay, well, so the y part of my normal force will be an up force, and the y part of my friction force will be an up force. So let's do just N for normal. So the y part of the normal force and the y part of the frictional force. My down force will be weight from gravity, Fg. And then left force will be the x part of the normal force, N standing for normal. And the right force will be the x part of the frictional force. So you should look at my free body diagram and notice how I figured out that Nx is left. So the normal force vector points to the left and up, so it has an up part and a left part. The frictional force points to the right and up, so it has a right part and an up part. So here are my equations for static equilibrium. But you might be thinking, well, why doesn't Mr. Melvin just go ahead and try to find what Ny and Ffy are by finding the y part of those forces? Well, the problem is I know this angle here, but if I draw my free body diagram on my box, looking for the normal force, I'm not sure what angle right offhand to use for the normal force. So let's go to the next slide. We're going to pause this thought process, and we're going to work through the angles in this problem and figure out what angle we need to use for the normal force. Okay, so the problem again is that if I have a normal force pointing at a right angle to the ramp, so there's a right angle here, I'm not sure that this angle applies to the normal force, and I'm not sure if sine and cosine apply to the normal force. So in order to figure that out, what I'm going to do is center an xy plane around my normal force. So I'm just going to do this to work through angles and see what happens. Okay, so now I'm trying to figure out what this angle right here on the normal force is, or I suppose I could also figure out what this angle here is. And I'm using different numbers of angle symbols just so that I don't get it mixed up with the one angle symbol right here. So let's take a look. I see, working my way toward the angle on the normal force, that theta, this angle here, and this angle here are going to be the same. And that's because I have two parallel lines, one here and one here, intersected by this diagonal line here. And I remember from geometry that alternate interior angles are the same, so this angle and this one are both theta. What I'm going to notice next is that if my normal force makes a right angle with the surface, that right angle is 90 degrees. And so this entire part from here to here is one big right angle. Therefore, if this part is theta, the rest of that kind of big angle has to add to theta to give me 90. So this second part here would be 90 minus theta, because together these two angles have to make a right angle, and they have to be 90 degrees. So if one of them is theta, the other is 90 minus theta. Next, I'll notice that since I drew an xy plane, there is a right angle between the x and y axis. And if the purple angle with green writing is 90 minus theta, and from here to here is also a right angle, that has to total 90 degrees. And if this part here was 90 minus theta, in order for that whole right angle formed by the xy axis to equal 90 degrees, the angle on the normal force must also be theta. So now I've figured out that the angle between the y-axis and the normal force is, in fact, theta. And from here forward, I give you permission to use that knowledge. If this angle is theta, the angle between your normal force and your y-axis is also theta. So let's move on and see how we use that. Okay, so here's what we know from the last slide. Our normal force makes an angle with a y-axis of theta. So now we've got to break apart our normal force in order to use it in an equilibrium problem. We have to break it into a y component, find the y component of our normal force, and we have to find the x component of our normal force, right here. So, let's think about this. If I want the y part of the normal force, I notice that y is adjacent to the angle itself. So the angle is in black there, right here, and y is adjacent to that angle. I also remember from geometry or trigonometry, so ka toa, and if you have an adjacent angle, use cosine. So the y part of the normal force then, in y, is the normal force cosine theta. I also see that if I brought up the x part to right here to complete my triangle for the vector, that the x component is opposite the angle, and when I have an opposite, I use sine. So the x component of my normal force in x is in sine theta, because the x part is opposite the angle. So the question was originally, how can I break apart the normal force into x and y parts? And now we've got that done. So here's where we were. We realized that f up was in y plus fy, and f left was in x, f down was fg, f right was f force of friction in the x direction. Well, now we can actually fill in what we've learned. We know that in y is in cosine theta, and in x is in sine theta. But now we have to worry about the frictional force. So let me draw friction as green here. So if we take our free body diagram and move it over here on top of the ramp, you can see that friction makes the same angle with respect to x as the ramp itself does. So friction will behave the way you normally expect. The sine part of friction will be y, and the cosine will be x, because if we were to draw an xy axis, y, x, the angle that the frictional force makes with the x is the same as what the ramp made. So friction will behave just like we're used to. So the y part of friction is the force of friction sine theta, and the x part is the force of friction cosine theta. And then, of course, we know that weight, or the force of gravity, is always m times g. And the question said, write the equations for equilibrium, which I've now done. N cosine theta, or the y part of n in this case, plus the y part of friction, F sine theta, equals our down force, mass times gravity, and then left and right forces. The x part of our normal force, or N sine theta in this case, equals the x part of the frictional force, FF cosine theta. You really need to understand how I got each of these parts, N cosine theta, N sine theta. This right here, you really need to understand. If you do not understand how to get that, if you're still like, wait, y is sine with x and y is cosine with y, if that's what you're thinking right now, you definitely need to rewatch this video before tomorrow. Because tomorrow we're going to hit the ground running with these problems, and if you don't understand how to do this example I just did, you will be completely lost. Once you've got all of this, though, it's just like the problems we've been doing before. Now you just solve for whatever the problem asks for. But you do have to be able to get this far. Alright, if you need to rewatch it, do so. If not, see you tomorrow.